We will start with the week 6 first lecture. Today we are going to study this section 9.5, which is the transmission of random process through a linear system. So previously we have studied some topics or definitions and their evaluations of these integrals related to PSD and autocorrelation and also random processes. So now we want to see that what if this random process travels through a linear time invariant system. So as we discussed in the early part of this chapter, that we don't have to deal with all sorts of higher order joint PDFs, because we will only be dealing with a linear time invariant system, which actually allows us to only assess a random process with its first and second order movements. So now we have a LTI system, and we will see how a random process responds when it passes through a linear time invariant system. Okay, so we are used to this method where when we have to pass a signal through a filter, then we often look into the either impulse response or the frequency response of the system, depending upon the convenience in whatever we were trying to do. So if you have a filter or any system that you can model, maybe it's a filter or it's some transmitter or some receiver, and you're just interested to know its Fourier transform, for example, if you're looking into the spectral component only. Okay, so if these systems, which can be again as just a filter, a transmitter or a receiver, if this is an LTI system, it actually makes our understanding of the system very much easy, because system that is time variant would not allow same kind of computations that we use in an LTI system. So if the system is LTI good enough, will be several points where we can compute some calculations that don't require some other complex tasks that are usually involved in a time variant system. So again, we have a LTI system. We hope we have an LTI system, and the signal that is passing through it is a random process x of t. And again, this random process we have not mentioned right now, but usually this random process would be at least wide sense stationary, as we discussed previously. So we did not write over here, but we are assuming that it's at least a WSS process, okay, a random process. So if it's an LTI system, then we know from practice and our previous knowledge that the output signal is actually the convolution of the input signal and the impulse response of the filter of whatever the system is. Okay, so that is how you calculate the output signal. So the output signal is definitely the impulse response of the is the convolution of the impulse response and the input signal. Okay, so this simple computation would give us the output signal. And if you want to calculate the output of the signal at some specific time tau, then again just replace this variable with, instead of writing t over here, we are writing t plus tau. So why am I writing two different terms right now? The reason is because I want to calculate the autocorrelation function of this output over here. Again, if you can connect, why do you think we are calculating the autocorrelation at this point? The autocorrelation of this signal, or the autocorrelation of the output signal, will actually help me in understanding the PSD of the output signal. Okay, so that is why I am interested in finding out this autocorrelation. So to find out the autocorrelation, I need to evaluate this expression. Again, same as before. So I have the definitions of y of t and y of t plus tau in the previous slide. So I can just replace or substitute these two terms over here, and this is the resultant equation that I'll get. And if I'll evaluate this equation, I actually get the autocorrelation function at the output. Okay, so if you look closely, what is happening over here, this is the convolution term, and this is the mean term, okay, or the term that is required in the autocorrelation signal, which is actually the mean of these two signals. Okay, so if you notice, this calculation, the computation of this mean, or you can say it's not exactly mean, because right now this because two variables are, or two equations are involved, this is actually giving us the correlation. So this correlation is applied on the variable t. Okay, just like if you have only one time domain signal, for example y of t, you can find out its mean, and that mean is actually a computation on the variable t. Similarly, the correlation is also computation on the variable t, and that variable seems to be missing over here and here. So whatever this integral is, the its correlation, or you can say simply its average value, would actually uh, it can be calculated quite easily, because if you notice, then this variable is missing t and this variable is missing t, and the average value of this variable based upon t is the constant itself, because it's a constant with respect to t. Okay, so if you notice, we have two different integrations going on. One integration is coming from this convolution, and the other integration is coming from this calculation of this mean. Okay, in both these computations, uh, in one of these computations, I'm sorry, the t variable is missing. In the other computation of this integral, the alpha variable is already there. Okay, and the beta variable is already there. However, in the calculation of integral where this time signal is involved, the time variable is missing. So for with respect to the time, this signal seems to be a constant. So when I calculate the average value of this signal, uh, the average value again of a constant is also a constant, so the answer will be h of alpha, and for this h of beta, the average value would still be h of beta. Okay, so I can simply write down these two values separately, because their average will return the same value even when you do calculate the average out of that integral of required for the average. Okay, so I'm left with two terms, this one and this one. Okay, so these two terms still remain, and the integral outside still remains. So I have not solved this integral with respect to alpha and with respect to beta right now. And you can also question this, that even though there are two separate integrals, for example this integral for convolution and another integral that we have not written but is required in this correlation computation, so there are two integrals, and you know that an integral is actually not dependent upon the order. So you can either use this integral first, I'm sorry, you can either use this integral first, or you can compute this integral first, and the order of integration does not matter. So it means that we could evaluate this integral first as well. So we did it, and we found out that this value was constant, so we wrote it down separately. Okay, so we would use this property because we can see that we are left with actually this variable, or this term actually, and if you notice, it is actually the autocorrelation of x, because both the signals that are involved over here are x. So it will return us the autocorrelation of x, but obviously you can see very clearly that the variable inside is not really t. It is t minus alpha over here, and it is t plus tau minus beta over here. So usually the correlation or the autocorrelation involves these two variables. Okay, so t and tau. However, this is not t, this is t minus a, and this is not t minus tau, this is t plus tau minus beta. So for our understanding right now, the value of t seems to be t minus alpha. Okay, so looks like as if this value is t minus alpha. uh, okay, so actually the value of, if you want to compare these two integrals, these two functions, then you'll notice that this, if this is equal to t, then this should also be present over here, so this should also be present over here, t minus alpha. So this should not be like this, in fact it should be something like this, t minus alpha. Okay, and obviously the other term that we can see is actually plus tau minus beta. So this is the whole term that is present over here. So if you write it down separately, you'll notice that these three values, the uh, integration or the autocorrelation seems to be being applied upon these values. So we don't just have tau over here. In fact, we have these three values right now. Okay, so these three values result in this computation that gives us this autocorrelation. Okay, so it's you can compare it with this typical variable of t and t minus tau, but the interesting observation over here is that the variable is not just tau over here. In fact, it is this whole variable that is involved. Okay, so you can write it down separately over here as well, that this autocorrelation function is actually not just a function of tau. In fact, it's a function of tau plus alpha minus beta. Okay, and to obviously, if you notice that this variable is not exactly equal to t minus alpha plus tau minus beta, it is actually t plus tau minus beta. So what is this the magic over here? The magic is that the term other than the term t is called the term tau. Okay, so this function must be equal to tau. However, this function is equal to tau minus beta. Okay, so this means that tau must have been equal to tau minus beta. I'm sorry, this mouse is not working well. Tau minus beta plus alpha. So if this is the value of tau, actually tau minus beta plus alpha, and we put this value over here in tau, then we get the actual answer. Okay, so because originally we wrote t as t minus alpha, and if we put tau as tau, which is plus over here, plus tau minus beta plus alpha, then the alphas would cancel out and we are left with t plus tau minus beta, same as written over here. So now you can notice that the value of tau is actually this tau minus beta plus alpha, and the value of t is actually t minus alpha. So I wrote it down over here. Okay, this is the value of t. Okay, so this is the value of t minus alpha, and the value of tau actually is tau minus beta plus alpha. So when the autocorrelation function is written, it is written as tau plus alpha minus beta, not just tau, as we usually write for this kind of autocorrelation. Okay, so this is what we write usually. Okay, but the tau is not exactly tau. In fact, the tau is equal to tau plus alpha minus beta. And at the end, when I just want to write out it as tau only, then I should know that tau is equal to actually tau minus beta plus alpha. So just in a summarizing way, I have written tau over here, but tau exactly equals to tau minus beta plus alpha. Okay, so this is the term, the autocorrelation term that I have for the output function right now. And if you notice, this is the autocorrelation of the x, this is the autocorrelation of the output, and I still have to perform this convolution. Okay, so this convolution is left. So I have two convolutions, so that is why you see in the result we have two convolutions. So one convolution is with this function and the other convolution is with this function. Okay, so two separate convolutions. So I write this down again. This is the autocorrelation function. Again, you know the meaning of tau. This is the autocorrelation function. This is the result of the convolution after or when we convolve it with beta, and this is the autocorrelation when we convolve it with alpha. So you can either say this is alpha or this is alpha. Both works because the function is actually the same, h. However, there is difference in the variable alpha and beta, and if you notice, alpha and beta actually in the autocorrelation function come with the opposite sign. Okay, so since they have the opposite sign, when you perform this convolution, for example, first with alpha, then you are actually kind of doing this calculation, h of t being convolved with the autocorrelation function of x. So this is the calculation that you are doing. However, when the beta comes, then this beta has the opposite sign over here. So just to correct it, you have to make the sign positive. Okay. So when you do this, actually you have to multiply the sign in the variable and you get the h of minus tau term. Okay, the same answer, just the term inside the variable is now negative to get the same meaning. So we have two convolutions involved over here and two functions only. One is the h and one is the autocorrelation, and we see a sign reversal because of that the reason that we have positive signs over here, but the sign is different over here. Okay, so if we want to produce if we, for example, if you want to convolve in this something like in this direction, okay, you flip the signal and you move it towards the right, then the opposite sign means that for one function you move it towards the right, but for the other function you moving towards the left. Okay, so just to make that correction, we have introduced this negative term which we could see over here. Okay, so this is the result of the output autocorrelation function, the output autocorrelation of y of t. So what do I do with this autocorrelation function now? I can calculate the power spectral density by taking the Fourier transform of this function. So if you remember from the exercise of the previous week, where when we wanted to find out the Fourier transform of this function, we use the same operation, that the Fourier transform, or when you expand this term, okay, it is actually equal to h of f into h of minus f. Okay, we did this exercise in the last week. Okay, so this is how the computation happened. So in the frequency domain, you are multiplying the two signals, and in the time domain, obviously, you are convolving these two signals. Okay, so again we can see the difference in this value. This is positive, this is negative. So obviously then this is positive, this is negative. So from when you move to time domain to the frequency domain, you will see that you will get the same result. Okay, so we know that this would result in this function. And what do we get with this? This is a autocorrelation of the x. When we take its Fourier transform, we get the PSD of x. So this happened because we were assuming that x is a Whiteson stationary random process, and its the Fourier transform, its autocorrelation function, would be equal to its power spectral density. So to calculate the power spectral density at the output, we are saying that we first need to know the power spectral density of the signal at the input, and whatever the transfer function is of the channel or the filter involved, you need to calculate this value and multiply it with the PSD to calculate the PSD of the output. So the PSD of the output is really dependent upon the input PSD and the transfer function of the filter. So now that we have studied one property, that is the how to calculate the PSD of the output function when a signal passes, a random process passes through an LTI filter, now we can see another feature of the random process, that we might have a case where we have a sum of two random processes. A typical example would be when our message is a random process, again assuming a WSS random process. So our message is a random process and a noise signal is added to it, and it is also a random process. Okay, so we have a sum of two random processes. Okay, so if we have a sum of two random processes, which is now called z of t, the autocorrelation of z of t will be given as such as this, same definition as we used previously, and now we will replace the value of z of t with x of t plus y of t in both these values, and this is the result that we get. Okay, so we have four total products happening over here. X of t will be multiplied with x of t plus tau, x of t will be multiplied with y of t plus tau, then yt will be multiplied with x of t plus tau, and then yt will be multiplied with yt plus tau. So when xt and xt plus tau are multiplied, we get autocorrelation of x. When y is multiplied with yt plus tau, we get autocorrelation of y. But when x is multiplied with y and the shifted version of y, it is not an autocorrelation, because we are not comparing x with itself. In fact, we are comparing x with another function y. So we call this simply correlation. So we have correlation of x and y, and when y multiplies with x, we get correlation of y with x. We get these 4 terms. Okay, if you notice that if x and y are uncorrelated, which means that x or y are two independent signals. So if again giving or continuing our previous example, if x of t is a message signal, it's a random process, and the noise is also a random process, then they are not correlated. They are independent of each other. They do not have any feature that is comparable or matchable, you can say. So they are uncorrelated. They are independent of each other. So if they are independent of each other, then from the properties of correlation that you must have studied in the previous course of probability, you know that you can find the correlation simply by multiplying the mean of x and mean of y for both these cases. Okay, so again, assuming them to be independent or uncorrelated, their correlation would be equal to the product of mean of x and mean of y. Okay, so this means that the previous expression would get simplified with this one term only. So now instead of 4 terms, we have these 3 terms. Okay, so this value can also approach 0 for one specific case, and that is if either this value is 0 or this value is 0. So we say that the mean of noise would be equal to 0, and that is a very common case when we assume that a noise is a 0 mean signal or a random process. So it is very common to assume, and so that is a popular case. Also, the message signal or a voice signal in communication can also be 0 means random process. That is usually the case. So for both of these variables, both of these values, the mean of x and the mean of y, there's highly likely that at least one of them would be equal to 0, again for only our purpose of communication. Okay, in our applications, one of these signals is usually 0, and when even one of these is equal to 0, even though both of them can be equal to 0, this value goes to 0. So we are left with only this. Okay, so the correlation, or you can say the autocorrelation of this sum of two random processes is equal to the sum of their individual autocorrelations. Okay, so you add the autocorrelation of x to the autocorrelation of y, and you get the autocorrelation of z. So that was relatively easy to find. So if you have autocorrelation function of your input functions, you can very easily calculate the output autocorrelation function of their sum. And if you remember that we are always interested in finding out the PSD, so if we take the Fourier transform, we get the PSD. The PSD of z would be equal to the PSD of x plus PSD of y, because we are only taking Fourier transform of this equation, and the Fourier transform of these two separate equations with these two separate integrals can be evaluated separately, and we'll get two separate PSDs, one from x and one from y. So if for the sum of two random processes, the PSD of that sum is actually equal to the individual sum of their PSDs. Okay, so again this is a function. However, if you are interested to calculate or compute the exact power of these PSD, then you know that you need to perform this integration. So if you integrate the PSD, you get the power. Okay, we did discuss this thing last time in the previous week, that if we integrate PSD, we get the total amount of power, and the total amount of power is also written as the mean square value for WSS process. So this means that if I integrate this term, I get the mean square value or the power. So the power is equal to the sum of these two individual powers. So if I have two random processes being added and I know their power, I can calculate the total power of their sum, which is simply equal to their sum. Okay, so this is one of another feature that we can use for weights and stationary signals. So whatever we had studied in this lecture, the most important thing is that you remember these small points, that if we have a WSS process or a stationary process, these kind of features or these kind of you can say properties are applicable, that we can add their individual powers, or their PSD would look something like this, and then autocorrelation function would look something like this, and the last previous thing that we studied in the slide, that the output PSD of the process that passes through an LTI system would look something like this. So these are some of the things that you need to remember, that will be useful for the computations that we will see in the future problems.